In this section, we will learn about the effect of different parameters on the fatigue properties of a material. Let us first start with the stress concentration factor due to presence of a notch. Now the presence of a notch in a specimen under uniaxial load introduces the following three effects. Firstly, due to the notch, there is an increase or concentration of stress at the root of the notch. Secondly, a stress gradient is set up from the root of the notch in toward the center of the specimen. And thirdly, a triaxial state of stress is produced. Now before proceeding further, it is important to remember about the theoretical stress concentration factor denoted by Kt, which is actually the ratio of the maximum stress to the nominal stress. The value of this stress concentration factor or Kt can be computed from the theory of elasticity for simple geometries and can be determined from photoelastic measurements for some complicated situations. Next, we come to the fatigue notch factor. The figure over here demonstrates the SN curves for both the notched as well as the unnotched specimen. In this figure, we can see that the fatigue limit for the notched specimen is lower compared to the fatigue limit for unnotched specimen. Now, the fatigue strength reduction factor or fatigue notch factor, as denoted by Kf, actually expresses the effectiveness of the notch in decreasing the fatigue limit. Here, the fatigue notch factor or Kf is simply the ratio of the fatigue limit of a notched specimen to the fatigue limit of notched specimen. Now, for materials which do not exhibit a fatigue limit, the fatigue notch factor is based on the fatigue strength at a specified number of cycles, as we have studied in the earlier sections. Now the values of Kf have been found to vary with several parameters like the severity of the notch, the type of the notch, material, type of loading and stress level. Now regarding the value of fatigue notch factor or Kf, two general trends are observed for test conditions of completely reversed loading. Firstly, Kf value is usually less than the value of Kt, and secondly, the ratio of Kt by Kf decreases as the Kt value increases. So this indicates that very sharp notches with high Kt value have less effect on fatigue strength than what would be expected from their high values of Kt. Regarding the effect of stress concentration on fatigue, lastly, we come to the notch sensitivity factor. Now the notch sensitivity of a material in fatigue is expressed by a notch sensitivity factor or index, which is denoted by Q and which is represented by this particular equation, that is Kf minus 1 divided by Kt minus 1. Now this particular equation was chosen so that for a material which experiences no reduction in fatigue due to a notch, where Kf equals to 1, it has a factor of Q equals to 0, and for a material in which the notch has its full theoretical effect, where Kf equals to Kt, it has a factor of Q equals to 1. Now, the value of Q is not a true material constant because it varies with the severity and type of the notch, the size of the specimen, and the type of loading. Over here, the figure demonstrates the variation of notch sensitivity index, that is Q, from 0 to 1 for different materials of different strengths, where the aluminum alloy has the lowest strength and quenched and tempered steel has the highest strength. The figure indicates that notch sensitivity increases with the tensile strength of a material. Thus, it is possible in certain cases to decrease the fatigue performance, that is, to increase the notch sensitivity index by increasing the hardness or tensile strength of a material, as revealed from this figure. This is about the notch sensitivity factor, which represents the effect of stress concentration on fatigue. Next, we will study about the effect of size and surface roughness of a specimen on the fatigue properties. Changing the size of a fatigue specimen usually results in a variation in two factors. Firstly, increasing the diameter increases the volume or surface area of the specimen. The change in amount of surface is of significance since fatigue failures usually start at the surface. Secondly, for plain or notched specimens loaded in bending or torsion, an increase in diameter usually decreases the stress gradient across the diameter and increases the volume of material which is highly stressed. Next, we come to the effect of surface roughness of the specimen. Now, smoothly polished specimen in which the fine scratches, which are actually the stress razors, are oriented parallel with the direction of the principal tensile stress, give the highest values in fatigue test. Such carefully polished specimens are usually used in laboratory fatigue test and are known as par bars. Here in this table, we can see that with the decrease of surface roughness of the specimen, the median value of the fatigue life in terms of cycles is increasing. So, this is all about the effect of size and surface roughness of the specimen on the fatigue properties. Next, we will learn about the effect of residual stress on the fatigue strength. For many purposes, residual stresses can be considered identical to the stresses produced by an external force. Thus, the addition of a compressive residual stress which exists at a point on the surface to an externally applied tensile stress on that surface actually decreases the likelihood or possibility of fatigue failure at that point. Over here, the figures indicate this particular effect. For example, the first figure shows the elastic stress distribution in a beam with no residual stress. Here we can see that the beam is under a bending moment denoted by MB. The stresses on the right hand side of the vertical axis are tensile or positive, while the stresses on the left hand side of the vertical axis are compressive or negative in nature. Now, due to this bending moment, the upper surface of the beam is having a tensile stress of plus sigma max, while the lower surface of the beam is having a compressive stress of minus sigma max. The second figure shows a typical residual stress distribution such as would be produced by a short pinning. We can see in this figure that the entire surface of the beam is having a residual stress of sigma r, which is compressive or negative in nature. Now, we may note over here that the high compressive residual stresses at the surface must be balanced by the tensile residual stresses over the interior of the cross section as shown in this figure. The third figure shows the stress distribution due to the algebraic summation of the external bending stresses and the residual stresses. We may note that the maximum tensile stress at the upper surface is reduced by an amount equal to the surface compressive residual stress. Here we can see that for the upper surface, due to the superimposition of the applied tensile stress and the compressive residual stress, the resultant tensile stress has decreased to sigma max plus sigma r, where sigma max is the applied stress which is tensile or positive, and sigma r denotes the residual stress which is compressive or negative. Now, the peak tensile stress is displaced to a point in the interior of the specimen as shown in this figure at this particular point. The magnitude of this stress depends on the gradient of applied stress and the residual stress distribution. Thus, the subsurface initiation of failure is possible under these conditions. On the other hand, at the lower surface of the beam, due to the superimposition of the applied stress which is compressive and the residual compressive stress, the resultant compressive stress has increased to sigma max plus sigma r, where sigma max is the applied stress which is compressive or negative, and sigma r is a residual stress which is also compressive and negative in nature. At this point, it is important to realize that a designer may be aware of the applied stresses but may not be aware of the residual stresses. Therefore, due to the superimposition of the applied and residual stresses, the resultant stresses, whatever is coming out, is very much critical and may affect on the fatigue properties and fatigue strength of the specimen. Now, it should also be apparent that the improvements in fatigue performance which result from the introduction of surface compressive residual stress will be greater when the loading is one in which a stress gradient exists than when no stress gradient is present. However, some improvement in the fatigue performance of axial loaded fatigue specimens results from the surface compressive residual stresses presumably because the surface is such a potential source of weakness. So, this is all about the significance and effect of the residual stresses on fatigue strength. We will now study about the effect of temperature on fatigue. Let us first study about the low temperature fatigue. Fatigue tests on metals at temperatures below room temperature indicate that fatigue strength actually increases with decreasing temperature. Fatigue strength exhibits a proportionately greater increase than even tensile strength with decreasing temperature. On the other hand, when we check the high temperature fatigue, we can observe that generally above room temperature, fatigue strength of metals decreases with increasing temperature. An exception is mild steel, which shows maximum fatigue strength at 200 to 300 degrees centigrade. Ferrous materials, which generally exhibit sharp fatigue limit in room temperature test, will no longer have a particular fatigue limit when tested at temperatures above approximately 430 degrees centigrade. As the temperature is further increased well above the room temperature, especially at high homologous temperature, that is T by Tm is greater than 0.5, creep becomes the principal cause of failure. The transition from fatigue failure to creep failure with increasing temperature will result in a change in type of failure from the usual transcrystalline fatigue failure to the intercrystalline creep failure. In general, higher the creep strength of a material, higher will be its high temperature fatigue strength. At any given temperature, amount of creep will increase with increasing mean stress. Also, fatigue test at high temperature will depend on the frequency of stress application as well. Continuing with the high temperature fatigue, at elevated temperatures, local grain boundary oxidation can contribute significantly to crack initiation. Fine grain size results in better fatigue properties at lower temperatures. As the test temperature is increased, the difference in fatigue properties between coarse and fine grain actually decreases until we come at elevated temperatures where creep predominates and coarse grain material exhibits higher strength. Metallurgical treatments producing best high temperature fatigue properties does not necessarily result in the best creep or stress rupture properties. Similarly, we can observe that procedures which are successful in reducing the fatigue failures at room temperature may not be so much effective in high temperature fatigue. When we study about the effect of temperature on fatigue, we must mention about the thermal fatigue. The stresses which produce fatigue failure at high temperature do not necessarily need to come from mechanical sources only. Fatigue failure can be produced by fluctuating thermal stresses under conditions where no stresses are actually produced by mechanical causes. Now, thermal stresses result when the change in dimensions of a member as a result of a temperature change is prevented by some kind of constant. For example, the simple case of a bar with fixed end supports, the thermal stress developed by a temperature change delta T is given by this particular equation, where alpha denotes linear thermal coefficient of expansion and E denotes the elastic modulus. Now, if failure occurs by one application of thermal stress, the condition is called the thermal shock. Whereas if failure occurs after repeated applications of thermal stress of a lower magnitude, it is called the thermal fatigue. Conditions for thermal fatigue failure are frequently present in high temperature equipment. Now, the tendency for thermal fatigue failure appears related to the parameter as shown over here, that is the term given by sigma f into k divided by E into alpha, where sigma f denotes the fatigue strength at mean temperature and k denotes the thermal conductivity. A high value of this particular parameter actually indicates good resistance to thermal fatigue. Now, austenite stainless steel is particularly sensitive to this phenomena because of its low thermal conductivity, that is K, while high thermal expansion, that is alpha. So, this is about the thermal fatigue.